going to do an overview of your exponential function characteristics notebook entry. So kind of summarizing things that you should have picked out from the gizmo. So when we look at an exponential function, and we've talked about a little bit about characteristics through the Desmos activities and then through the gizmo. We're looking at that general format is going to be y equals a times b to the x power. So why is this called exponential? Because our variable, the x variable, our independent variable, is part of the exponent. So there are some specifications, and you don't necessarily need to memorize these, but have an idea of why these would be. The first one is that the a value cannot be, not 1. The a value cannot be 0. The reason being is if a was 0, imagine that you had a 0, y equals 0 times 2 to the x, that would just be 0 times anything is just 0. So that would just cancel out the entire thing and wouldn't be a very useful function. The second part here is that b needs to be greater than 0, but cannot be equal to 1. Or shouldn't be equal to 1 because if I look at, for instance, let's just do a little simple function. If I made the b value 1, the reason it can't be 1 is because now I have 1 to a power, I have 1 to the second, 1 to the third, 1 to the fourth. If I plug in numbers for x, 1 to any power is just going to be 1, so that's not really going to change my value. Then the reason that b needs to be greater than 0 is if we put negative numbers in here. So let's say I did -1 and I start doing powers. If I do -1 to the second power, and then I do -1 to the third power, and I do -1 to the fourth power, you have a positive, and then a negative, and then a positive, and then a negative. What will happen is your values keep jumping back and forth between positive and negative. So we're only going to deal with positive values there. Again, those are not necessarily things you need to memorize, but things that are going to be important as you're looking at the functions. So in this equation, the a and the b value, what you're supposed to pick up on the gizmo is that these have meaning, these have areas where you see them over and over again in your graphs. And when it comes down to it, what the a value is telling you is this is what would be termed your, this will be useful to you when we talk about writing equations to show situations, this is your initial value. In other words, how does it show up on your graph? What you should have noticed is that your y-intercept of your graph for any equation is, and remember, what do we know about a y-intercept? A y-intercept has a 0 value for x. Your y-intercept should be 0, comma, that a value. The reason being is, I'm going to take off to the side here to show you why really quick, is because if we plug in, like we said, what do we know about a y-intercept? It has a 0 as an x value. If I plug in 0 for x, and I do the exponent first, b to the 0 is 1, so a times 1 is a. Whenever you do the y-intercept for this type of equation, you're always going to be left with just that a value left over, because anything to the 0 power is 1. So the a value, that initial value, shows your y-intercept. The b value, which we call the base, is the repeated factor. And when we say factor, remember that factor means this is what we are multiplying by. Factor means involving multiplication. So b is the value that we're repeating over and over again. So we're talking about folding a piece of paper in half, like we did with the moon example that we did. That repeated factor was 2. We were multiplying by 2 over and over and over again. So when you are looking at how your value is changing, that's that b value, the repeated factor. So like when we see times 2 times 2 times 2 times 2, dot, 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 that translates into that 2 to the x. Like that's where that base comes from, because we can just rewrite that as a power. So when we're looking at our equations, there's a few things that we're going to be able to pick out. And one is whether our graph is going to be considered to be a growth, an exponential growth, where our graph is increasing. So your sketch doesn't need to be perfect, but looks something like this. Or is it a decay where our graph going from left to right is decreasing? So there's a sketch of a decreasing graph. And what determines that is whatever we're going to be doing that repeated multiplication with. So our b value determines if it's growth or if it's decay. How do we get growth? What you should have noticed on the very first page of your gizmo in the warm-up is that if your b value was a number bigger than 1, that your graph was always going to be increasing. If your growth factor, well, now it's a decay factor, would be between 0 and 1, which we can write in our inequalities like we learned this way. 0 is less than b is less than 1. It's between 0 and 1, then your b value is telling you are decreasing. The nice thing is, whether you're increasing or decreasing, there are certain characteristics that are going to stay the same. The first one is the domain and the range. For the domain, if I look at all the x values on my graph, notice I have arrows on the ends. These are going to continue left and right forever, in both cases, left and right. So for the domain is always going to be all real numbers. And I'll draw the symbol in as well. For the range, looking at our range, as far as the arrow goes, we have this arrow on both of these that are going to go up. So as far as the top end of our range for our y values, there isn't a highest value. The highest value is going to be infinity. But if you notice the lowest value, and this is the part we're going to talk about with this word that follows, the lowest value there only goes to, but doesn't actually hit the x-axis. So if we talk about the range here, the range for our y values are going to be greater than 0, but doesn't actually get to 0 because we have this value or this line called an asymptote. So what an asymptote is a line the graph approaches. So in other words, gets closer and closer and closer to. The graph approaches, but never touches. So the x-axis, and for our cases, for both growth and decay, if you notice on the right side of decay, the graph goes down and down and closer to the x-axis, and the left side of the growth, the graph goes closer and closer and closer to the x-axis, but never quite gets there. The reason being, just to give you a really short explanation, is think about the x values here for these different points. Like here's an x value of -4, -5, -6, -7. Let's pretend the equation of this graph is y equals, just a simple one, y equals 2 to the x. If I plug in 2 to the -1st, 2 to the -2nd, 2 to the -3rd, that's 1/2, that's 1/4, that's 1/8. What do you notice about these numbers? Let's do 2 to the -10th, 1 over whatever 2 to the 10th is. What do you notice about those numbers as my x values keep going to the left, get smaller and smaller and smaller, is that my y values, these values are getting smaller and smaller as well. In order for that to actually hit the x-axis, you'd have to get all the way to 0. So you'd be looking for a number, when I take 2 to some number, that's going to get me equal to 0. The answer is that actually can't happen. There is no number. You're going to get smaller and smaller and smaller digits, or numbers, but you're never going to get all the way to 0. So that is what is called an asymptote. The graph approaches that line, but it never actually touches it. So for us, it's the x-axis, which can be written as an equation as You remember your horizontal and vertical lines, and I'll just write this in so as a reminder. You probably don't need to write that in, but HOY, a y equals is a way to write a line equation of a horizontal line. So the equation for the x-axis is y equals 0. Now, as a final piece here, as a characteristic that we look at in other functions, there is no x-intercept because the graph approaches the x-axis but never touches it because of that asymptote. The graph approaches the x-axis but never crosses. Never crosses or touches it in any way. So those are the big characteristics that you need to be starting to notice off of exponential equations, and that are going to help us do two things. They're going to help us, well, three things. We're going to write equations, we're going to graph equations, and we're going to write equations for situations. The main thing you're going to worry about right now is just graphing an exponential. To graph it, we're going to go kind of back to basics when it comes to doing a graph. To graph an exponential, you're going to identify points, and notice I have a table here. You especially want to identify the y-intercept, and you're going to graph those points. The one thing you want to remember as you are graphing is your asymptote. So when you're drawing your graph, you might want to just go ahead and a dashed line is how we show an asymptote on a graph. But you might want to go ahead and just throw your asymptote on there so that you remember your graph is not going to cross that. That's one of the specifications for a quality graph, is that you're not going to actually cross that line. You're going to get close to it, but you're never going to actually cross over it. So when we make our graph, when we do our graph here, we want to make a table. We're going to just pick our own values. So what I'm going to suggest in general is, oops, that's the positive one, is that you would make your graph, you would choose your x values to go from -2 to +2, just as an easy way to kind of regulate which points you're getting and kind of staying around the x and y axis as much as possible. So when you're looking at this, you want to try and pick out your characteristics here. You have an a value of 3. You have a b value of 2 when you think about your y equals a times b to the x. That a value, again, reminder, tells you the y-intercept. So your y-intercept is 0, 3, and I'm going to put that on my graph. And your b value, that's your base. That's telling you what your multiplication factor is that you're going to be repeating over and over and over again, that you're using as your base to your exponent. The asymptote is at y equals 0. It's that horizontal line. And then how do we determine whether it's at growth or decay? You determine your b value. Your b value is 2, and if b is bigger than 1, think about this. I'm going to be repeating, it's 2 to the x, so I'm going to be repeating 2 and 2 over and over again, multiplying by 2. So this is going to be a growth factor. Pardon me. So how do I get other points to go on my graph? Well, I'm going to go ahead and start plugging them in. So if this is my x value, and I'm going to start with my positives, I'm going to do 3 times 2 to the first power to get this value. So I'm going to do my exponent first. 2 to the first is 2 times 3. So this should be 6. So 1, 6 goes on my graph. I'm going to take my next x value. X is 2. So this is 3 times 2 to the second. That's 2 to the second is 4. 3 times 4 is 12. Now 2, 12 doesn't fit on my graph, and that's okay. If it's not going to fit on my graph, you could do a scale if you want to, but I think we're going to have enough points as it is. So for -1, I'm going to do 3 times 2 to the -1st. 2 to the -1st is really 1/2. So this is 3 times 1/2, which is 3/2, which is 1.5, 1.5. So I have -1, 1.5. And then for my last one, 3 times 2 to the -2nd. That's 3 times 1 over 2 to the second, which is 1/4. So that's 3/4, which is about 0.7, which is 0.75. So I'm going to put that on my graph as well. In order to, and I'm going to pick a different color, in order to graph this, you just want to connect the points and stay respectful to your asymptote. You're going to try the other one on your own. The fraction makes it a little bit more tricky, but then you're going to check the answer key for accuracy.